Good morning, Switzerland, and good evening, Japan. It's a great pleasure to have Naonori Ueda Sensei for this particular talk on machine learning and AI seminar series for RIKEN and CIS. Naonori Sensei received his bachelor's, master's, and PhD degrees from Osaka University. In Japan from 82, 84, and 92. In 84, he joined the Electrical Communication Laboratories NTT Japan, where he was engaged in research on image processing, pattern recognition, and computer vision. In 91, he joined the NTT Communication Science Laboratories. From 93 to 94, he was a visiting scholar at Purdue University. In 2010 to 13, director of NTT Communication Science Laboratories as well. He was the head of the NTT Machine Learning and Data Science Center he has been the head of the NTT Machine Learning and Data Science Center since 2014 and the director of Ueda Research Laboratory since 2016. He engaged in research on image processing, pattern recognition, statistical machine learning, and data mining. Since 2016, he's a deputy director for Center for Advanced Intelligence Project RIKEN, where he engaged in AI research on medical science, weather, natural sciences, such as disaster prevention and reduction, and social science based on machine learning technology. He's a research supervisor, Mathematical Information Platform, Japan Science and Technology Agency, CREST, and is a visiting professor at Kyoto University Graduate School of Informatics and Kobe University Graduate School of System Informatics. Now, it's a great pleasure to have you again here, Naonori Sensei. I'm looking forward to your talk.
Thank you, kind introduction. So today, let me introduce machine learning technology for disaster prevention and mitigation. Okay. So let me briefly introduce myself. I've been working at NTT Basic Research Laboratory, and I'm also work at RIKEN AIP at the cross appointment. At NTT, I've been doing research on machine learning based on the Bayesian statistics, especially non-parameter based. And these are recent papers. So also, you may be interested in these papers, but today, I'd like to introduce a recent research result of the disaster resilience science team at RIKEN. Okay. As you know, Japan has suffered tremendous natural disasters, including major earthquakes, tsunamis, and typhoons. So the disaster prevention and mitigation are important social issues in Japan. So I established this team to solve these social issues by AI technologies. So currently in my team, there are 9 researchers, 3 are expert in earthquake, and the others are machine learning researchers. So, of course, this research requires expert knowledge and data from experts. So we are collaborating with a foreign organization to conduct our research. I mean, the National Research Institute, Earth Science and Disaster Resilience, Japan Meteorological Agency, Earthquake Research Institute, University of Tokyo, and the RIKEN Center for Computational Science. This center has a Fugaku, you know. Okay. We are conducting research and development of AI technologies on the following topics: the earthquake damage evaluation to evaluate how much damage will occur by megaquake, and earthquake occurrence forecasting, focusing on non-pi-trap historical sequence prediction. Okay. Also, we are conducting research on automatic generation of hazard maps for landslides and flooding by using machine learning technology. And also, we are conducting the weather forecasting with collaboration with JMA, and focusing on high accurate weather forecasting, and also a typhoon intensification prediction using the machine learning technology. So today, I'd like to introduce the following topics. Especially, I elaborate a bit on the third topic, including the formulation. Okay, And for the others, I only give a brief outline of a few ongoing research topics. Okay, this is the first topic, a megacorp damage simulation by HPC and AI. Okay, so this research is a ground motion simulation technology by supercomputer and machine learning. So, of course, simulation is very important for inland earthquakes, because if we can estimate how much damage will occur to buildings, so we can reinforce those buildings in advance. So why difficult? So because soil at depth of 100 meters from the surface has a complex geometry that changes every 10 meters. And also ground shaking due to earthquake becomes highly nonlinear. So conventionally, nonlinear wave equation is simulated by supercomputer using a 3D soil structure. Okay, these are soil. So more accurate simulation requires more accurate 3D soil structure data, but boring is time-consuming and costly. Moreover, the presence of buildings and other structures makes boring impossible. Okay, so therefore, traditionally, Monte Carlo approximation was performed on inaccurate 3D soil structure data by running thousands of simulations for each point and average them. This is the typical Monte Carlo approximation. Okay. So to address this problem, we achieved extremely efficient simulation by using a convolutional neural network as a surrogate model. So first, we perform simulation by changing evaluation values for a small spatial area. And then we divide the simulated data into a smaller leveled spatial data. So this level means, for example, class 1 means lowest damage, and class 5 corresponds to the highest damage. So next, we train the CNN by using this label data in supervised way. And finally, we predict the fault areas by using the trained CNN. So this means that the CNN becomes a surrogate model for simulation. Okay. So I'll show you the result. The left figure shows the result on the supercomputer, and the right figure shows the result of the proposed method. Okay. So column map shows the magnitude of the shaking. So as you can see, the results look almost the same, but the amount of the computation time was reduced to about 1/3000. Okay, very efficient. And also, this table is a quantitative evaluation result of the proposed method. So, in the proposed method, we formulate as a clarification problem. So case A shows the classification error rate as a simple 5+ problem. In the case B evaluation, if the classification is misclassified as an adjacent class, it is considered correct. That's the optimistic evaluation. For example, even if class 2 is mistaken for class 3, it means that there is no significant difference in the damage of the earthquake. So it is regarded as a correct answer. So anyway, we got a very nice result. So, and I'll show some demonstration. Okay, so this demonstration is a simulation of shaking that would occur if Tokyo were hit by a magnitude 8+ earthquake. Okay, this is just a simulation, not real, of course. So this is the ground surface and the ground structure. Okay, and this is a simulation result. And the red areas indicate greater shaking. Okay, so clearly, so magnitude of shaking depends on the ground structure, very non-linear. Of course, since it is meaningless to simulate only the shaping of the ground surface, the building model is used to simulate the shaping of the building as well. So through simulation, it's possible to know which building is dangerous and take measures such as reinforcement in advance. So in this sense, this type of simulation is very important. Okay. Okay. So very recently, we have developed a more advanced simulation method. I mean, specifically, when solving differential equation using the green function based method, it's necessary to find the calculate the green function. But for nonlinear differential equations, it's very difficult to find calculate the green function analytically. So in contrast, we have made it possible to efficiently solve the green function by using DNN as a surrogate model. So the result of this research were fortunately awarded in some international conference. Okay, so using Fugaku. So let's move on the next topic, Nankai Trough historical sequence estimation. So the area where the Philippine Sea plate and the Eurasian plate meet to form a trench-like topography on the seafloor is called the Nankai Trough. Okay, so this plate boundary along the Nankai Trough, Philippine Sea plate is subducting beneath European plate at a rate of several centimeters per year. The plate on the land side that has improving reaches its limit and it's lifted up, causing a huge earthquake. Okay. So since this process occurs repeatedly, so Nankai Trough earthquakes occur repeatedly. So our challenge is to estimate the recurrence intervals for Nankai Trough earthquake. The right figure shows the sequence of megaquake recorded in Nankai Trough consisting of 3 regions, Nankai, To-Nankai, and Tokai, over about more than 1,000 years. Okay, you can see that Nankai megaquakes have occurred at irregular intervals with large variations. Okay, so conventionally, based on the friction laws between the plate and the interaction cells, the megaquake cycle have been simulated to reproduce the historical record. And if the estimated cycle is consistent with the past cycle, so future occurrence may be predictable. So, and cycle simulation can be formulated by this asperity model showing this partial differential equation. So it's very quite technical, so I don't explain the details, but the important thing is that this equation contains unknown parameters that depend on the location, AI, BI, and LI. So, so it cannot be simulated without setting these parameters. Okay. So, and many researchers have so far manually adjusted the friction parameters, controlling the recurrence intervals to reproduce such complex megaquake cycles in the simulator. Here the set parameter values based on the various information. But it's shown this result. Desired results were not obtained. So actually there is an error nearly 50 years between the Hoei and Hansei earthquakes. Okay. So we propose a method based on the new approach to this problem, which I call a simulation-based machine learning. Let me explain more. So in general, machine learning, you know, especially deep learning, requires a large amount of training data. So machine learning is difficult to apply when there is not enough observation data, as in the case of a major earthquake. So on the other hand, mathematical models such as differential equation or partial differential equations have been studied in the science field. So, but they are not perfect, not complete, because they include unknown parameters such as friction parameters, I said. So simulation-based machine learning is to complementarily combine these two. And that is, training data is artificially generated by simulating with a mathematical model by varying the parameters. And learning machine, such as DNN, is trained to inversely estimate the parameters from the data. After learning, the unknown parameters of the mathematical model can be estimated from a small number of observations because the relationship between the parameter values and the simulated data has already trained. Okay. Okay, I'll explain in detail in this program. So we know the reasonable range of parameter. So we change the parameter value within that range and run large number of simulations. So we have pair of parameter value B and time series slip velocities. Then we try to inversely estimate the parameter B hat from a set of slip velocities by minimizing this objective function. So maybe you can see DNA can be used to do that. But there's a problem. I mean, this task was not so simple because slip velocity cycle can vary widely even when the difference in B values is very, very small. So naive end-to-end DNA didn't work well. We found that. So to address this problem, we propose a cost-defined learning approach as shown in this figure. Suppose that we have a set of slip velocity cycles generated by A simulated by changing parameter B. So given a set of slip velocity cycles and DNN roughly predict target value B based on the classification and magnify the range. Okay, so then DNN try to reduce the residual magnified R in a fine-grained manner. So I'll skip the detail, but we also extended this idea to a more general anchor-based regression problems. Okay. So this slide shows the result. This histogram shows the histogram of errors in the estimated B value. And the prediction error cycle was also obtained as follows. First, by inputting the cycle data of the past Nankai trough data to the DN after training, and we obtain B values. And then we generate the cycle data by simulation with the B value and calculate the error between the generated cycle data and the past true cycle data. So you can see our method could provide a much more accurate estimate than the naive DNA. So this result demonstrates the effectiveness of a simulation-based machine learning approach. Okay. Okay, let's move on the third topic. So as for this topic, I explain in more detail, including some mathematical formula. Okay. So next topic is related to CMT inversion analysis using Gaussian process. Okay, Gaussian process is still very hot in machine learning community because it's very general and not DNA. Okay. So the stress state in the Earth crust is crucial to generation of earthquakes. So direct measurements of the state the costly and the limit to the shallow part of the crust. So the stress state is frequently estimated from other sources of information. So the centroid moment tensor CMT analysis has been used as an indirect method. Okay. So the conventional CMT analysis is based on the basis function expansion method. And so the computational cost is order M cubed. M is the number of model parameters. On the other hand, our new approach based on the GP can reduce the computational cost because the number of model parameters is much larger than the number of observations. I'll explain that later. And further advantage of formulation is that the covariance function GP is derived analytically, not in ad hoc manner. So I'll explain detail. Okay. So first, let me review the CMT analysis because you are not familiar to this kind of stuff. So CMT analysis is an inverse problem that estimates cluster stress tau at the crust from the stress tensor Y at the surface. So physically, the cluster stress causes the ground surface stress according to this equation. Okay. So CMT analysis is an inverse problem of estimating the cluster stress tensor from the observable stress tensor at the surface. So quite important. So because by estimating the stress tensor in the crust, it's possible to estimate the location of future earthquakes. Okay. And Yij is a stress tensor at position X. And I and J are tensor indices. Okay. I mean in three-dimensional world, X, Y, Y, Z, and ZX planes. And for each plane, X, Y, Z, three directions. So in principle, CMT has 9 component tensor. But for symmetry and other reasons, it is represented by a seismic sphere with only 3 components. And furthermore, in convention for visual understanding, it's represented as a pattern, so quantified into 5 types of visualization. Okay, these symbols. And capital A is the size of earthquake and is computed by the seismic moment depending on the magnitude of the earthquake. Okay. So let me pass the conventional approach. Terakawa and Matsura, 2008, solved this inverse problem using the method of basis function expansion. The stress field is expressed as this linear combination tau by x over m fixed basis function with a vector of a model parameter A. Okay. And observation equation and prior information are expressed in terms of probability distribution A. Okay. And using the Bayes rule, we can obtain the optimal vector A hat and the shear of A hat by using the simple linear algebra. And this is a common method that is still in operation today. But clearly, inverse matrix calculation is computationally extensive, as you know, on the order of the cube of m. And m is usually on the order of several thousand or 10,000. Okay, so this approach was difficult to analyze on a large scale. Also, as will be shown later, 4D CMT, 4D means including the time evolution analysis is not possible in principle. Okay, so in contrast, the proposed GP approach can solve these 2 problems. Okay, I'll explain this. Okay, let me explain the formulation by GP. I explained how the CMT analysis is formulated by GP. The first, I explained the forward model as a regression model. That is, forward model means the problem is to estimate the stress tau asterisk at an arbitrary position x asterisk. So suppose that the unknown stress field tau x over a Gaussian process, so with a mean function and a covariance function. And this means that tau x at arbitrary finite end positions of a multivariate Gaussian distribution shown in this equation. Okay, where mu and k are our prior knowledge on the stress field tau x. Okay, I mean, for example, mu mean function should be 0 because this means the stress shows no preferred direction a priori. And the k, xi, and xj can be formulated to this equation. This means that so stress field are smoothly varied with the characteristic amplitude sigma s and the correlation length sigma l. Okay. So, and also the prior distribution of stress tau at the single position x asterisk is assumed to be Gaussian. Okay. Then suppose that we obtain a direct measurement of the cluster stress D, and with observational error sigma l, and seek estimate tau asterisk at arbitrary position x asterisk. So according to the model assumption, this one, the joint distribution of D and the tau asterisk is given by this equation. Okay. So where Aij and these covariance function evaluated at data and estimate positions. Then using the formula of conditional distribution of a Gaussian distribution, the posterior distribution of tau asterisk for given data D is easily computed as this equation. It's also very simple calculation. And so optimal value of the hyperparameters sigma s, sigma l, and sigma n, so determined by maximizing the marginal likelihood in the conventional way. Okay. So next, I'll explain the CMT data inversion using Gaussian process. This is a very important point on this formulation. So let me explain in more details. Suppose that we obtain the CMT solution, the n aspects D children. Okay. Then the joint distribution of D children and the tau asterisk would be written as the Gaussian. Okay. But the major difference from the previous regression formulation is that the two physical quantities, y and tau, these are stress, are involved in the single expression. So I mean, we should clarify the 2 points. One is the mean and covariance function of CMT solutions must be properly defined. And other one is so different kind of variations, tau and y, must be treated in the cross term. Okay. So as you know, in the case of a normal regression problem using Gaussian process, we can consider the covariance function the one single space. For example, if two inputs are very close, the corresponding output are also close, and so Gaussian kernel is used for that case in some other manner. On the other hand, here we have two different surfaces, geographical surface and fault surface. Fault is danso in Japanese, okay? And so we need to consider not only the covariance function in each space, but also the covariance function between the two spaces. Okay. So I explained that there is a relationship between the two spaces through this physical equation. Okay. So actually using this relationship, So we can analytically derive the kernel function between the two spaces. This is the important point in this formulation. I'll explain in more detail, okay? So first, let me explain the mean function. Using observation equation, this observation equation, the mean function is computed as. So because expectation value is computed only on the random variable dependent t term, so moreover, its expectation becomes 0 because we assume stress shows no preferred direction a priori, so as a prior distribution. So very easy, okay? And similarly, from the physical equation and the fault stress assumptions, Kij can be calculated analytically as follows. Using the equation 1 and 2, Kij can be calculated as from the definition of the covariance function and the equation 1, we obtain this equation. And after rearranging the equation and using the equation 2, we obtain this equation, and finally we got this result. Okay, because exponential integral is very easy to compute. Okay. Also, I skipped the detail, but the cross term of the covariance function can be calculated similarly. Okay, no approximation. Okay. So the remaining components are calculated in the same way, and finally obtain the joint distribution D and tau. Okay. So it's important to note that the mean and the covariance function obtained analytically from the CMT equation without manual setting. Okay. So calculating the posterior distribution of the tau from this equation, we can estimate the CMT inversion. Okay. So this table summarizes the differences between the conventional and the proposed method. So as I said, M is much larger than M. M is the number of model parameters, and N is the number of data. Okay. So GP approach is much more efficient than the conventional method. Okay. So also, we apply the conventional method and our method to real data. Specifically, we apply the areas which were particularly active after the Tokai earthquake in 2011. You remember this one, maybe. The spacing of the basis function was set at 20 kilometers horizontally and 10 kilometers vertically. Okay. And the left figure shows the earthquake distribution, and the right figure shows the observed stress on ground surface. The number of observation points was 2,423, and the number of basis function was set to 9,375. Okay. So this figure compares the result of a CMT inverse analysis using the conventional state-of-the-art method. And this is the basis function method and the proposed method. Okay. As you can see from these figures, storage results are almost the same, but computational time of method was reduced by the factor of about 60. They're very efficient, very fast. So since cluster stress is not measurable, only God knows. So it's difficult to quantitatively evaluate the estimation result. But the GP method could get results similar to those obtained by using a basis function method. And the basis function method had already been validated on artificial data. So we can say that GP-based formulation is useful in the sense that it can much more efficiently estimate cluster stress than the basis function method. Okay. So this figure shows the application results for the entire Japanese anti-parallel parabol. GP method can efficiently calculate the entire Japan at once whereas the conventional method will not. So although the period is different, we confirmed that the stress field are generally similar to those in previous studies published in the paper. Okay. So, and also our GP approach can be easily extended to time evolution model. That is, covariance function of time-dependent stress field and the covariance function of the time-dependent CMT solution as follows. For the lack of time, I won't see the details today, but I showed some result. So in fact, we applied this method to the time evolution of the stress field. The estimation result is shown in this figure. You can see the dominant change is estimated at the edge of the source region of the Terakawa earthquake. Okay, so in addition, the following observations. Okay, these observations can be made from the result of this estimation. With the lack of time, I won't detail, but we found that many informative fine findings obtained from this analysis. Okay, so let's summarize this study. This study can be summarized as follows, but I'll not read it out due to the lack of time. But I think that this study is also important achievement in that it was solved efficiently by surrogating physical equation with machine learning technique, in this case a GP. Okay. Okay. In the rest of the time, I briefly introduce about the 3 ongoing studies. Okay. So this research is in collaboration with the Japan Meteorology Agency. So in recent years, extensive damage caused by a strong typhoon has become an issue. Okay. For example, typhoon number 10 in Japan in 2021 caused a record-breaking wind and heavy rainfall. So many houses were damaged. Currently, Japan model developed in the US and a partially modified version is used to forecast typhoon intensification. Okay, so this model estimates the temporal change in the central pressure of a typhoon from about 24 environmental features such as sea surface temperature and total humidity and so forth. So this table shows the result of several models and compared with the current JMA model. And so intensifying typhoon is defined as a typhoon drops 20 hectopascal in central pressure after 48 hours and formulated as a problem to judge the whether it's intensifying typhoon or not. Okay, so we have considered a variety of models and have found a slight improvement in accuracy over the current GMA model, but it's not sufficient and is currently undergoing refinement. Okay, GMA model use only environmental features, but where takes a multi-model approach using satellite images at the same time. Okay, and this research is also a collaboration with JMA. In JMA, 3 numerical forecast models with different temporal and spatial resolutions integrated to provide a more accurate weather forecast. Okay, this is a real operation in Japan. And that is a temperature, precipitation, and the wind forecast. Currently, the JMA is using simple average in actual operation. Of course, some Bayesian averaging or some other method has been proposed, but these are not unstable. So the JMA uses this simple average. So we are developing a more advanced method to improve the weather hope with the JMU. Okay. And this is the final topic. This study is holding cluster dislocation. The model is generally expressed by a partial differential equation. Conventionally, the solution was obtained by the boundary element method or the finite element method. So, however, the boundary element method requires a green function, which is computationally infeasible for materials with non-linearities. And the finite element method requires discrete relation. In a mesh, there are so many meshes it requires. Okay, therefore, the theoretical analysis of infinite regions is impossible. So, on the other hand, we have developed a complementary new method, new approach, modeling based on physics-informed neural networks. So specifically to deal with discontinuity, we transform to a polar coordinated system. This modeling can flexibly represent arbitrary geometric structures and mechanical properties of rocks, which cannot be achieved with the existing method. So furthermore, it has a outstanding feature that can be extended to inversion analysis, origin state, process, and purpose. So recently we submitted a paper to Nature Communication and is currently under review. Okay. So I think these results are very valuable to RIKEN AIP because we can demonstrate how machine learning technologies can contribute to the development of scientific research. Okay. Okay, it's time to stop. Thank you very much for your attention.
Thank you, Naonori-sensei. Are there questions for Naonori-sensei? Ueda-sensei? So one thing that I thought was interesting is that you end up showing these examples from, let's say, earthquakes. How do you have access to this particular data? Is this publicly available?
Yeah, so some governmental organization has this kind of data. Also, some data is available, or
I mean, to me, this is very interesting. I think these particular events need to be studied, and you have shown that machine learning techniques are quite good in predicting, but has scalability challenges.
Yeah.
And with a bit of work, we can scale and do the predictions. So this is very nice. So thank you very much.
Yeah. So reason why we are collaborating with some organizations, some experts. Yeah.
I think this is a must and a great idea.
Yeah, and also, so fortunately, AI is very passionate. So they asked us, is it okay? Is it useful for AI and to this kind of stuff? Yeah.
Fantastic.
We are very interested in using the AI. Yeah.
Okay, so are there questions?
May I also ask a question?
Yes.
So, about simulation-based machine learning. So this is really a fantastic idea, and somehow it's related to like self-supervised learning. But now we have a physical simulator, so it must be much more reliable.
Yeah.
But my question is, so how do you validate the trained model? Because now data is artificially generated, and we have never access to the true data.
Yes. But so we have a small amount of real data from observation. But I said before, of course, DNA can deal with such a small data. But we, on the other hand, we have some mathematical model. So scientists developed, theoretically these models. Then they combine these mathematical models and a small amount of data. And also we can simulate artificially simulated data from the mathematical model by changing the unknown parameters. Then we try to, compare the result, generated data, and a small amount of the real data. So kind of a data assimilation.
I see.
Yeah.
So
yeah.
how about the first? So you showed us the simulation video of earthquake in Tokyo, and that looks quite realistic and nice. But how do you also evaluate it?
Evaluate. Evaluation means is that simulation is correct or not?
Yeah.
Okay.
Because once you slightly change the initial parameter, maybe the shake pattern may change a lot.
Because we compare the result between the result obtained by the supercomputer only, and also we compare the our proposed our result by the proposed method. So the results are almost the same. Yeah. In this sense, approach is effective.
I see. So because this is my basic question, for simulation. Like in machine learning, we always validate our model based on cross validation or based on some validation data. But the simulation people, they just generate some prediction and say that it's real, it's close to real, but no real validation. Like COVID-19 simulations are quite artificial, for example.
Yeah. So in this sense, we should combine these two. Yeah.
I see.
Correlation.
So in a sense, the contribution is both. So machine learning can benefit from simulation, and also simulation community should also benefit from machine learning community.
Yeah. So we have to communicate each other. Yeah.
Thank you very much. That's great.
Yeah. Thank you very much.
Okay, I think there is a question in the box by Kibin Zhao Sensei. I'm wondering if these real-world applications have potential reliability problems such as adversarial attacks.
So question was why then, if there are real-world applications have potential reliability problems such as adversarial attack. So adversarial attacks is very important issue in this recently.
I think that the kernel-based approaches would be a little bit robust to these kind of attacks. But that the neural network ones would have some problems.
Yeah, I think so.
So
sorry, I don't really understand the question. So
I guess that the question refers to the fact that when you have your data, if there is an adversary perturbing the data, perhaps that the system that you're using or building to do the predictions may have robustness issues or reliability issues. But I mean, this is a grand challenge in machine learning directly, and I think that this is a problem that we all need to think about. Maybe not just in this particular instance.
Yeah.
Well, other questions for Uedo Sensei? All right, this is then perfectly on time. So thank you very much for your talk. And well, looking forward to the next talk series. So have a great evening in Japan and have a great day in Lausanne and Switzerland. Yeah.